In this video, we are going to talk about a way of expressing sets called set builder notation. We're first going to review the rule model for describing sets. We're going to define set builder notation, and we're going to show some examples. So first, remember that the rule model for sets is that a set is a rule that tells us what items are in the set, and of course, which items or elements are not in the set. So what our set builder notation does is it takes this rule model and gives us some syntax for writing out what this rule is. So it allows us to efficiently define a set as a rule. So what do we need to do? Well, it needs to tell us what kind of elements are in the set, right? That's our universal set, and that's going to be kind of reminiscent of the domain of discourse that we were talking about back when we were doing quantitative statements. It then also has to tell us the rule that is satisfied by elements in the set, right? So it's a two-part process. And the syntax for that is whatever the set is equal to, on the left, we have to say what kind of element it is, what the universal set is. So X is in the universal set. And then on the right-hand side, it's X satisfies some rule. So remember, we got to tell two things. What the universal set is, that's on the left. What rule it's satisfied, that's on the right. And those are separated by a colon. So here's one example that we've seen before. Let F be the set of people in my immediate family. So first of all, we got to determine, well, what's our universal set that we're going to specify our attention on? Well, it's going to be the set of all people. We're talking about people in my family. It makes sense to narrow things down to just people when we're thinking about who's in the set. And then the rule is, well, the person has to be in my immediate family, right? So I'm going to look at all the people. Each person, are you in my immediate family or not? If the answer is yes, you're in the set. If the answer is no, you're not in the set. So here is how our set builder notation is going to look. First of all, I'm going to specify P to be the set of all people, right? Because that's my universal set. And so our set builder notation is going to say that our set F is equal to the set of all X in P, right? P is our universal set, so the set of all X in the set of people, such that X is in my immediate family. So here is a more mathematical example, maybe, or a more numerical example at least. Let's see if we can use set builder notation to define the set of odd numbers. Now, the first thing we want to do is narrow our attention to a universal set. We're talking about odd numbers. That means that they're a special type of integer, right? We don't want to be looking at fractions or irrational numbers for odd numbers because that's not a very fruitful set to look at. And then we have actually two possible rules depending on how you want to describe odd numbers and what you're using them for, what the purpose is. We won't get too much into those things here. That's more appropriate for a proof class. But one possible rule is, well, if you have an integer, how do you tell whether it's odd? Well, it's not, one way is that it's not an even number, right? So what you do is you say, well, here's what an even number is, an odd number is not that. Another way you can say it is that the odd integer comes right after an even number. So it's an odd integer could either be an integer that is not an even number or comes right after an even number. And that gives us two possible ways to have set builder notation. So if we use the not an even number example, we're going to say that D is the set of X in Z, X in the set of integers, because remember, the integers form our universal set, such that, well, X is not an even number. If we want to use the comes right after an even number definition, we can say that D is the set of all X in the integers. That part's going to be the same. Our universal set is still the set of integers. But now, how do I say that X comes right after an even number? Well, I'll say that X is equal to, well, it's not going to equal to 2K, but 2K is how we'd express an even number, right? It's twice some other integer. And then to say it comes right after it, I'll add a plus 1. And I can't just let K be any old number. K has to be an integer in order for this to work. Because if K were 1/2, I'd get 1 plus 1 is 2, which is not an odd number. K has to be an integer. So all x's that are in the integers such that x equals 2k plus 1, where k is some integer. All right, well, now I have two sets of activities for you to look at that are associated with this video. One of them is called Element in Set, and one of them is called Set Relations and Operations, and those are both PDF files included with this video.